This video introduces the derived rules. The 6 named rules that I have listed here are best thought of as shortcut rules. In our basic system we have 10 rules, 2 for each of our connectives, an in rule and an out rule. That basic set of rules is a complete system, and in theory we wouldn't need anything other than those 10 basic rules. But if we stopped with just those 10, many proofs would be very, very difficult, and the derived rules basically make life easier. The 6 rules that I have listed here are the ones that I think it's most valuable to know. But the truth is, some textbooks list lots of other types of shortcut rules that you could use, and in theory, there's really no limit to the number of rules that you could have. Any proof that you can do, you can adopt its form as a rule. In fact, to call these things derived rules is to say that they can be derived from the basic rules. Let's see just one example. Repetition is the first rule. We already introduced repetition in class, and we've been using it since early in the semester. The rule says that if you have P on one line, you can get to P on another line. So as an argument, it's especially simple. If you use repetition, you would just say 1R. But if you didn't have repetition, you could still do this. In fact, the easy way would be to say, of course that's our assumption, you'd be stuck at the top, and so you'd go to the bottom and see that there were no connectives. You'd make a box. You would assume tilde P. That would be a PA for tilde out. And then you would be looking for a contradiction, but of course you would immediately have a contradiction with P and tilde P, and so that would be 1, 2, ampersand in. That's a pretty lousy 2 right there. And now you'd be done. 2 through 3 tilde out. Now, the only reason I did this is because for every one of these rules, you could construct a proof to show that the rule is legitimate, and you would use just our previous rules. All right, so let me get rid of this. What I'm going to do in this video is just talk about all of the other rules and give simple illustrations of them and try to get you comfortable with the rules. All right, so repetition. You've already got that one memorized. Notice that double negation is just about as easy. Double negation, which we'll abbreviate DN, says that if you have tilde tilde P on a line in your proof, you can write P. In other words, you can drop 2 tildes at any time you want. Notice that I represent this rule and repetition and a few of the others here with a double line. This double line denotes that this is an equivalence rule, and that means that you can go either direction. So you can drop 2 tildes, or if you want to, you can add 2 tildes. On the side here, I present the rules in the ways that will actually make use of them. And for double negation, it's actually useful to drop 2 tildes, and sometimes it's useful to add 2 tildes, and so that's why I represent it twice. Just representing it once would be sufficient, but I want to represent the rules in the way that you want to know them. This is an incredibly simple rule. I'm guessing you already understand it. Notice that if you have a formula like tilde tilde A arrow B, this rule, let's say you had that on line 1, then that would have let you write this as A arrow B. You can drop 2 tildes whenever they are the main connectives for the formula. I think of this as an automatic rule. When you've got 2 tildes outside parentheses, that's something you immediately want to do. When I have 2 tildes on a single letter, say like tilde tilde S, I'm usually not in a big hurry to drop those 2 tildes. I know that this is the same thing as S, and if I see that I need S someplace else in the proof, I can drop them at that time. All right, Double negation, also an incredibly easy rule. Not likely that you'll have trouble with that one. Now let's look at DeMorgan's and arrow exchange. These three rules, notice there are two versions of DeMorgan's. These three rules are some of the most useful that we introduce. DM stands for DeMorgan's. Augustus DeMorgan was a pioneer in propositional logic in the mid-1800s. He thought a lot about the relationship between the wedge and the and his name is frequently associated with this relationship. DeMorgan's works on tilde p wedge q and also on tilde p ampersand q. I like to show arrow exchange at the same time. It works on tilde p arrow q. Obviously, the similarity between these three lines, these three formulas, is that they all have the tilde as the main connective. Up until this point, the tilde as the main connective in a proof is a lock on the parentheses. And so there's nothing that you could do with these formulas up until now. All three of these rules are equivalence rules. That's why they have the double therefore bar. But for the most part, you won't want to think about using them except in the direction that they're illustrated. Now, if you're really good with proofs and you like to be creative, every once in a while you'll see an opportunity to use these backwards, and it might save you a bunch of time. But for the most part, you should really just concentrate on them on the way that they're presented. Here's how they work. For the two DeMorgans, notice there's a wonderful symmetry. And so for both of them, I like to say what you do is switch the connective, wedge to ampersand, or ampersand to wedge, and then you distribute the tilde. And distribute is just a fancy word for add it to both parts. So tilde p wedge q turns into tilde p ampersand tilde q. But tilde p and q, well, switch the connective and then distribute the tilde. So tilde p wedge tilde q. If you're going to remember the rules, I think one of the best things that you can do is to associate a story with each one so that you make the rule meaningful. For instance, this first one I might say, it's false that I enjoy puzzles or quizzes. It's false that I enjoy puzzles or quizzes. That means that I don't enjoy puzzles and I don't enjoy quizzes. This one says it's false that I enjoy both puzzles and quizzes. So in other words, I don't enjoy puzzles or I don't enjoy quizzes. In terms of symbolization, you should recognize that both of these forms of DeMorgan's mean negate both parts. And these forms both say negate just at least one part. Arrow exchange is a little bit different. For arrow exchange, the arrow turns into an ampersand, and then the P comes down without any changes, and the Q part gets the tilde. This might be the least intuitive of all the rules. For a story, the one that I tell for myself is that this says it's false that if you're a prince, then you will grow up to be queen. So you're the prince, but you don't grow up to be queen. It's false that if you're a prince, you'll grow up to be queen. You're the prince, and you don't grow up to be queen. I really think that when it comes to doing proofs, understanding the rules is the key. And probably one of the best things that you can do for yourself to learn these rules is to make yourself rewrite them and plan to write them on the test. And probably the best thing to do to get yourself to the point where you can actually do that is to invest every rule with some meaning. Let's see some practice examples of how these things work. So let's say you were doing a proof and on line 1 you saw the following. Tilde A wedge B ampersand C. Can you apply any of these three rules to this line? The answer is certainly yes. As soon as you notice that the tilde is the main connective, from now on that's good news. whenever you see the tilde as the main connective, you should immediately be thinking, well, that's going to either be DeMorgan's or arrow exchange. Notice there is one small possibility that there is one possibility that can arise. What if you saw tilde P double arrow Q? Well, in that case, there's not a derived rule that we have to apply. We actually could give ourselves several different possibilities, but the textbook that I was using didn't offer a possibility for this, and I've discovered that it's kind of nice not to remedy that situation, because now if I want to give something tricky, there's still this opportunity. But if you see a tilde outside parentheses in any other case, well, that's great news. Okay, so we see the tilde as the main connective. Afterwards, when you notice that, you immediately ask, what's the main connective inside the parentheses? And of course, it's the ampersand. And since it's an ampersand, we're obviously doing this version of DeMorgan's. Well, we switch the connective, and then we distribute the tilde. So we would get tilde A wedge B, wedge, tilde C. Switch the connective, add a tilde to both parts. That's all there is. That would be line 2, and the justification would be 1 DeMorgan's. All right, let's see another couple of examples. Get this one out of the way. And then imagine that you've got the following. We've got tilde, parentheses, tilde R ampersand S, wedge, tilde, tilde T. Well, this is getting kind of messy, but do any of these three rules apply? The answer is definitely yes. The tilde is the main connective. And what's the main connective on the inside? It's a wedge, so we're doing the first version of DeMorgan's. The rule says switch the connective and then distribute the tilde. Now, tilde, notice the P part is everything that's between the first parenthesis and the wedge. The Q is everything afterwards. P, Q. The P's and the Q's are merely placeholders, and given where the P is at here, you can see that it's everything between the first parenthesis and the wedge. Well, that's exactly what this is, so it's P. P has a tilde built into it. If we're going to follow this rule exactly as it's written, then what we're obligated to do is add a tilde to P. This tilde on the outside, in effect, it gets distributed. It goes in two places. So what we do is say, well, obviously the P part now has to have a tilde added to it, so we're going to get tilde tilde R and S. On the backside, the Q part had two tildes in it. But the rule says we're supposed to add one, and so what are we going to end up with? Tilde 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 T. 3 tilde T's. And so that would be line 2, and the justification is 1 dm. Now you might be saying, well, do I really have to add those two tildes? We know that it's the same thing. R and S is the same thing as tilde tilde R and S. And that's true. We know it's the same thing. But if we're going to follow the rule very rigidly, then we have to add a tilde when we do DeMorgan's. We have to add a tilde to both parts. Of course, notice, look what is the payoff for having done DeMorgan's here. We get an ampersand. So if you were actually doing a proof, then you would want to break this up on lines 3 and 4 and get tilde tilde R and S. And then you would get tilde 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 T by 2 ampersand out. Now, having done both of those things, you could have then, of course, applied double negation to lines 3 and 4 if you wanted to. So now you could get R and S on 5. That would be 3dn. Add or subtract 2 tildes any point you want, and obviously we're subtracting 2 tildes right now. And then on line 6, what would triple tilde T turn into? it would be single tilde t, and that would be for double negation. Right? So notice with these new rules, we're oftentimes able to take a long line like this and basically deconstruct it. A very handy thing to do. Well, let's look at one more example. Let us say that we have the following. Doing a proof, and on line 1 you have tilde r arrow d arrow tilde a. Can you apply any of these three rules to this line? Well, what's the main connective here? The main connective is the arrow, and so the answer is no. You can only use these three rules when the tilde is the main connective. Now you might say, well, can I just work on the front half by itself? No, our system always operates on main connectives, so if you're going to apply a rule to this, it would need to be a rule that works on arrows. So nothing you can do with it. But if I add some parentheses like that, now can you apply one of these three rules? And the answer should be yes. Tilde is the main connective, arrow is the main connective on the inside, so now we're doing arrow exchange. Remember, for arrow exchange, the arrow turns into an ampersand. The P part comes down as is. In fact, when you're using this rule, you will never even change a parenthesis on the P part. The whole thing should come down exactly as it is. And then the Q part gets a tilde. You might think of it as the tilde in the front runs over to the Q. And so Q had a tilde on it already, so what we're going to end up with is tilde tilde A. And that would, of course, be one arrow exchange. Now the next step, of course, would be to do an ampersand out, and then you could end up doing a double negation as well if you wanted. Next, let's take a look at Modus Tollens. Modus Tollens obviously works on arrows. MT is the abbreviation. It works on P arrow Q. Before I talk about it anymore, let's contrast it with arrow out. We know and love arrow out. To do arrow out, it says if you see a conditional, P arrow Q, if you find P on another line by itself, then you get to write Q. The traditional name for arrow out is Modus Tollens. You'll notice that for the derived rules, we are using the traditional names, Modus Tollens, DeMorgan's, Disjunctive Argument. But for our basic rules, we've been using these newfangled in and out names. But the traditional Latin name is Modus Tollens, which means something like the mood or the mode of putting or affirming. Modus Tollens is the mood or the mode of denying or taking, if you will. We don't want to confuse it with arrow out. This rule says if you have the negation of Q, then you get the negation of P. Here's a story to make this one make sense. If you're a porcupine, then you have quills. If you don't have quills, then you're not a porcupine. It makes especially good sense if you think of it in terms of necessary conditions. This basically says having quills is necessary for being a porcupine. So if you don't have quills, then you're not a porcupine. Let's take a look at a couple of examples. Imagine you're doing a proof and you have A arrow B on line 1, and then on line 2 you have tilde B. Can you use Modus Tollens on this? Well, obviously you can. Here's how you should think of things. From now on, every time that you see the arrow as the main connective, first of all you think about arrow out. And you say to yourself, well, if I can find an A on another line, then I can write B. And you take a look. If you do not find A, then you say, well, I also have to think about modus tollens. And to do modus tollens, you just need the negation of Q, whatever it is. And so Q here is B. So yes, we have tilde B. Therefore, the rule says we get to write the P part plus one more tilde. That means we get to write tilde A. And the justification, of course, is 1, 2, modus tollens. We can tell by looking at the rule here, that you're going to need 2 lines of justification, because just like arrow out, modus tollens involves a relationship between 2 lines. All right, this is really not a difficult rule to use, but let's see another example. What if you saw the following? On line 1, you've got R arrow S. And then on line 2, you have tilde R. What do you get from those 2 lines? Be careful, this is a trick question. When you're looking at line 1, to do arrow out, you would need to have an R. Well, we don't have R, so we can't do arrow out. To do modus tollens, you have to have the negation of Q. So you would have to have tilde S to make progress. Having tilde R does you no good whatsoever. The point here is don't start getting these 2 rules confused with each other. Modus tollens and arrow out work very differently, and having tilde R does you no good. Another example. Let's say that we have the following on a line in the proof. So on line 1, you've got tilde E arrow tilde D. And then on line 2, you have D. Can you get anything from those 2 lines? All right, we think about arrow out first, and if we had tilde E, we could do arrow out. Yeah, but obviously we don't have tilde E. So what would you need for modus tollens? You need the negation of Q. What would the negation of Q be? Well, if we're going to be really strict about the rule, the negation of Q would actually be tilde tilde D. We don't have tilde tilde D, but we do have the next best thing, which is D, and since we have our double negation rule, when I look at line 1 and I see line 2, I am inspired to add 2 tildes to it in this way and call this 2 double negation. Now that I have done that, I can actually do modus tollens on line 1, and what do I get? Tilde tilde E. And the justification will be 1, 3 modus tollens. I think this is a very important example. Let me see if I can try to be really clear about what just happened. For modus tollens, I'm going to put circles around P, and I'm going to put squares around Q. Notice if I do that, the only thing that's left out are the connectives. Now, that's pretty obvious because our rules just are P's, Q's, and connectives. But what I want to emphasize is that P and Q are just placeholders for whatever comes outside the connectives. When you look at line 1 and you see that the arrow's the main connective, well then you immediately know that everything in front of it is P and everything after it is Q. So here's P arrow Q, P arrow Q. According to the rule, if I'm going to make progress, I need to have tilde Q. Is D tilde Q? Well, it's not. D is the opposite of tilde D, but it's not what I really need. The rule says I need one more tilde than the piece that I'm working against. I think that's probably the thing to have in mind. You always have to have one more tilde. The reason is because notice, if I put a square around the Q part, you now see that I really do have tilde the Q part. So P arrow Q, tilde Q, therefore I get to write tilde P. P itself already had a tilde, and so that's why I wrote tilde E. Look at the circles and the squares and the connectives. Circle, circle, square, square, and then an arrow and two tildes. Every time that you use a rule in our system, it should always be possible to map the circles and the squares onto the actual proof so that it lines up in exactly this way. I hope that that point made sense, because I think drawing the circles and the squares can be very helpful to really get a grasp of what's going on with the rule. Well, we've got one more rule to look at, and I suppose we might as well do it. That's disjunctive argument. The last rule here. A disjunction is a wedge, so not surprisingly, disjunctive argument works on wedges. It has two forms, but they're obviously very, very similar. What does P wedge Q mean in terms of the truth of the parts? It means that at least one part is true. All right, so when you say P or Q, you're saying that at least one of these things is true. Either I'm going to make pie or I'm going to make quiche. Well, if I'm not going to make pie, then I guess I'm going to make quiche. So I say, look, for Christmas I'm going to make either pie or quiche. Well, I'm not going to make pie. I don't have any fruit. Therefore, I'm going to make quiche. At least one of these is true. If it's not the P part, it's got to be the Q part. Or, what if you know that I'm not making quiche? Then clearly, I am making pie. Every time you see a wedge as the main connective in your proof, you should basically say to yourself, at least one of these things has to be true. Let me see if I can find either part with an additional tilde. If I do, then I get to bring down the other part. You see, it says P or Q. Well, it ain't the P part. It's kind of like the tilde P is telling you cross off that, and then therefore you get to bring down the Q. Here's P or Q. Well, it ain't the Q part, so bring down the P. Oftentimes I don't like these crossing off metaphors that people use when they think about proofs, but I think in this particular case it's very appropriate. One part or the other has to be true. It ain't P, it's got to be Q. And if it ain't Q, it's got to be P. So let's look at a quick example. You see on a line that it says A or tilde D wedge E. And then on line 2, you've got tilde A. Do these two lines go together so that you can use disjunctive argument? Yes, they absolutely do. If the wedge is the main connective, everything in front of it's P, everything after it is Q. So this just is P or Q. At least one part has to be true. Down here we see it ain't A. Okay, it ain't that one. Therefore, it's got to be the Q. So we'll write tilde D wedge E. And that would be 1, 2, disjunctive argument. Another quick example. On line 1, you see tilde R. We'll have fun with tildes here. And then on tilde R or tilde S ampersand L. Why not? Just looking at this line, what do you immediately know that you'd have to find on another line in order to make progress? Well, that's P. This is Q. According to the rule, you have to have the negation of one half or the other. So literally, looking at this, you know that you would either need to find tilde tilde R, triple tilde R, right? You'd have to have one more tilde. If you found triple tilde R, then you could write tilde S ampersand L. But if you found tilde S and L, then you could write the other one. So let's say that on line 2, what I had was tilde S and L. I got lucky and I found that one right there. Well, so at least one of these two has to be true. It ain't that one. It must be tilde R. Justification 1, 2, DA. Notice we have a DA, a DM, and a DN. There's lots of D rules in our system. Okay, at this point we have introduced these rules, talked about some simple examples. What you want to do is practice rewriting the rules, take the quizzes and the practice exercises, which will build familiarity with the rules, and then you want to do some proofs. And as you do proofs, keep the rules in front of you and keep looking back at them as you work.